Some of NASA's heliophysics missions have been uniquely equipped to observe regions of the sky in extremely close proximity to the Sun, a capability that allows scientists to track celestial objects that would otherwise be invisible from Earth due to the Sun's blinding glare. This rare observational opportunity was leveraged when Comet 3 I/Atlas, an interstellar visitor, passed behind the Sun as seen from Earth. Such a position renders the comet impossible to observe using conventional ground-based telescopes, which are limited by both atmospheric conditions and the overwhelming brightness of the Sun. To overcome this challenge, NASA relied on a suite of specialized space-based observatories that are specifically designed to study the Sun and the heliosphere, the vast bubble of charged particles that the Sun emits throughout the solar system. Among these missions, NASA's Stereo Solar-Terrestrial Relations Observatory spacecraft provided a vital contribution. Between September 11th and October 2nd, Stereo continuously monitored the comet's movement, capturing images that revealed subtle details of its path and the structure of its tail. The data collected by Stereo not only filled observational gaps left by Earth-bound telescopes, but also allowed scientists to construct a more accurate three-dimensional trajectory of the comet as it traversed the inner regions of our solar system. In addition to Stereo, observations from the ESA, European Space Agency, and NASA Joint Mission SOHO Solar and Heliospheric Observatory added another layer of critical information. SOHO's instruments, designed to study the Sun's corona and solar wind, observed 3 I/Atlas from October 15th to 26th. These observations were particularly valuable because SOHO's coronagraphs are capable of blocking the direct light of the Sun, creating an artificial solar eclipse that makes it possible to see faint objects in close solar proximity. This technique revealed structural features of the comet's tail and coma, giving researchers insight into the behavior of interstellar material as it interacts with the intense solar radiation and solar wind. The addition of images from NASA's newly launched Punch polarimeter to unify the corona and heliosphere mission, which began operations earlier this year, provided further unprecedented detail. Punch's observations from September 20th to October 3rd allowed scientists to track the comet's tail as it stretched millions of miles through space, offering a rare glimpse into how an interstellar object reacts when exposed to the environment of our Sun's outer atmosphere. While NASA has a long history of observing and discovering thousands of comets within our solar system, the purposeful observation of an object that originated outside our solar system marks a significant milestone in heliophysics and planetary science. Interstellar objects like 3 I/Atlas provide a unique window into the composition and dynamics of other star systems, as they carry material that has not been previously processed by the Sun's gravitational or magnetic influence. Observing these visitors in detail allows scientists to compare them with comets formed within our own solar system, potentially revealing differences in chemical composition, dust-to-gas ratios, and other physical characteristics. Understanding these differences is crucial not only for studying the origins and evolution of comets, but also for improving our knowledge of planetary formation and the distribution of organic materials in the galaxy. In a remarkable demonstration of multi-mission collaboration, NASA's deep space spacecraft, Psyche and Lucy, were also able to observe 3 I/Atlas while traveling to their respective asteroid targets. Psyche, which is en route to the metallic asteroid of the same name, conducted 4 separate observations over an 8-hour period on September 8th and 9th from a distance of approximately 33 million miles. These images were instrumental in refining the comet's trajectory, allowing scientists to predict its path with far greater precision than would have been possible using only Earth-based or near-Earth observatories. Similarly, the Lucy spacecraft, currently studying Trojan asteroids near Jupiter's orbit, captured a series of images on September 16th from an impressive distance of 240 million miles. By stacking these images together, researchers were able to produce high-resolution views of the comet's coma and tail, revealing subtle details about its structure and activity that are otherwise difficult to discern at such extreme distances. The discovery and early observations of 3 I/Atlas were facilitated by several other key facilities. The comet was first detected on July first by the ATLAS, Asteroid Terrestrial Impact Last Alert System, telescope in Chile, which is part of a NASA-funded network designed to detect potentially hazardous asteroids and other celestial objects that could impact Earth. Following this initial detection, NASA's Hubble Space Telescope provided further observations later that month, offering higher-resolution imagery that allowed astronomers to study the comet's nucleus and tail in detail. The summer months of August saw additional observations from both NASA's James Webb Space Telescope, which is capable of observing in the infrared spectrum, and SPHERE-X, spectrophotometer for the history of the universe, Epoch of Reionization, and ICE's Explorer, which captured imagery designed to investigate the composition and spectral properties of the comet's material. Collectively, this coordinated observational campaign demonstrates the power of combining data from multiple instruments across different wavelengths and positions in space, enabling scientists to build a comprehensive picture of a transient interstellar visitor. As Comet 3I/Atlas continues its journey through the solar system, it is expected to make its closest approach to Earth on Friday, December 19th, at a distance of approximately 170 million miles. This distance, nearly twice that between the Earth and the Sun, poses no threat to our planet, but it does provide a unique opportunity to study the comet as it travels past the inner planets. NASA's fleet of spacecraft will continue to observe 3I/Atlas over the coming months, tracking its trajectory as it moves outward toward the orbit of Jupiter, which it is projected to reach in the spring of 2026. These ongoing observations will help scientists monitor changes in the comet's tail and coma over time, offering insight into how solar radiation, solar wind, and gravitational interactions with planets influence the behavior of interstellar objects as they pass through our solar system. The study of 3I/Atlas has broader implications for both planetary defense and our understanding of interstellar matter. By observing how the comet interacts with solar radiation and the solar wind, scientists can refine models that predict the behavior of other small bodies entering our solar system from distant star systems. These models are essential for preparing for potential future encounters with interstellar objects, whether they are cometary or asteroid in nature. Moreover, the detection and tracking of such objects illustrate the growing importance of international collaboration in astronomy and space exploration. Missions like SOHO, STEREO, PUNCH, and the observations from Psyche and Lucy highlight how coordinated efforts between multiple agencies, instruments, and observatories can maximize the scientific return from rare celestial events. The detailed imagery captured by these missions also provides valuable information about the composition of 3I/Atlas. For example, by studying the light reflected and emitted from the comet's coma and tail, scientists can determine the presence of water ice, carbon-based compounds, silicate dust, and other materials. Understanding the chemical composition of interstellar comets may offer clues about the building blocks of other planetary systems, including the potential for organic molecules that could seed life. This information can help place our solar system in a broader galactic context, showing how materials are distributed and recycled throughout the Milky Way. Furthermore, the techniques developed to study 3I/Atlas are advancing the capabilities of future heliophysics and planetary science missions. Observing objects near the Sun requires precise instrumentation, innovative imaging techniques, and careful coordination among multiple spacecraft, all of which contribute to improving the technology and methods used for other challenging astronomical observations. Lessons learned from tracking this interstellar visitor can be applied to detecting near-Earth objects, monitoring solar phenomena, and planning missions that venture close to the Sun or other bright celestial objects. The experience gained from this observational campaign strengthens NASA's overall ability to respond to both scientific and planetary defense opportunities, ensuring that the agency remains at the forefront of exploring and understanding our dynamic cosmic environment. In conclusion, the observation of Comet 3I/Atlas represents a remarkable achievement for NASA and its international partners. By utilizing a combination of heliophysics missions, deep space spacecraft, ground-based telescopes, and space observatories, scientists have been able to monitor an interstellar object with unprecedented detail as it passed behind the Sun and traveled through our solar system. This collaborative effort not only enhances our understanding of the physical and chemical characteristics of comets from other star systems, but also demonstrates the power of modern space exploration tools in uncovering the secrets of our universe. As 3I/Atlas continues its journey toward the outer reaches of the solar system, the data collected will provide invaluable insights into the nature of interstellar objects, their interactions with the Sun, and their potential significance for planetary science, astronomy, and the study of our cosmic neighborhood. The ongoing observations of 3I/Atlas will undoubtedly enrich our knowledge of the universe and inspire future missions to explore the distant and mysterious reaches of interstellar space.